Independent component design assumes zero correlation between failures as a source of safety. Statistical independence between failure modes is treated as sufficient to eliminate common risk. This assumption shapes redundancy architecture and reliability analysis. Independence is one property of the joint failure distribution. Absorption by a failure threshold is another. Correlation between component failures measures the tendency of failures to co-occur. It describes linear dependence between failure events. It does not measure the proximity of any individual component to its failure threshold. Correlation and absorption are structurally different objects. Independent components can each independently degrade to failure. Each component follows its own degradation path toward the same absorbing failure boundary. No synchronization between components is required for system-level failure. Independence does not remove the existence of individual component failure thresholds. Each component failure is a pathwise event. One component failing does not require other components to fail simultaneously. Absorption occurs along a single component degradation trajectory. Correlation across components is irrelevant to whether any individual component is absorbed. Independent components each face absorbing failure states with their own probability over time. The joint probability of all components failing simultaneously is not required. Each independent component faces its own absorbing degradation boundary. Independence distributes the timing of component failures. It does not prevent them. Common cause failures defeat the independence assumption in system design. Power loss, thermal stress, or environmental loading act on all components simultaneously. Reducing pairwise failure correlation does not eliminate shared physical stressors. System reliability is not component independence. Safety requires that absorbing failure states be structurally unreachable for each component under all operating conditions.